Okay, so this is talking about the electric field vector associated with a point in space and a charge. So what we're going to have is we're going to have some charge, and let's say it's negative, and we have some point in space. Let's call this point A. And we're going to have a vector that goes from the charge to the point in space. We're going to give that a name. So let's say it's R. Let's call this point 1. So it's R1A vector. And so vector R1A is going to have an X component with the I unit vector plus a Y component with the J unit vector. In this particular example, R sub X would be positive and R sub Y would be negative. So there we go. So that's the vector. Now, this charge is going to have some value, charge Q, Q1. So it turns out the electric field vector is going to be either towards here, so it's going to go this way, or it's going to go that way. So it's always aligned with the line that goes between the center of the charge and the point in space. Now, if it goes this way, it's being attracted, so this would be a negative charge. So if this was a negative charge, it'd be the one that goes this way. If this is a positive charge, then it's going to go the other way. And this R1A is in the direction of as if this were a positive charge. So if we have a positive charge, you want it to go in the same direction as this vector R1A. But if it's a negative charge, then it goes in 180-degree difference. And it turns out the equation for the electric field vector, so we'll call this E1A. So E1A is the electric field vector due to charge 1 at point A. And that's equal to the Coulomb's constant times Q1. So it's positive or negative. So in this case, we don't use the absolute value. Then we multiply by the vector R1A. We divide by the magnitude of R1A squared. So this is the length of the vector. That gives you the, we have K, Q over R squared, where R is always a positive number. Now, so this gives us a magnitude of the electric field. If we take the vector from Q1 to point A, that's a vector, but what we want is a unit vector. So also to get this into a unit vector that's in the same direction as R1A, we just divide by the magnitude of R1A. So now you see we've got the magnitude of R1A squared and the magnitude of R1A, so you can make that into cubed. So the final equation for the electric field vector at point A is KQ1, or whatever the Q is, divided by the magnitude of R1A cubed times R1A vector, like that. So let's get a piece of graph paper to show you how you do this. So we need some graph paper. So I'm going to switch these points just so they're not, you can see that it works no matter which way you're going. So let's pick a point A, which is over here. So that's point A. Let's pick a charge here. We'll pick a negative charge. Okay, so let's use a charge of negative 1.9 microcoulombs. And the vector from Q to point A, which is this vector, we can either use the coordinates or we can, so let's do it both ways. So this is just looking at the diagram and use count. 1, 2, 3, 4, 5, 6, 7, 8. So R, the R vector from 1 to A is going to be equal to, how many that was? It was 1, 2, 3, 4, 5, 6, 7, 8, minus 8I, minus 1, 2, 3, 4, 5, 6, minus 6J. So that's the position vector. The other thing you could do is you could take the coordinates, which are going to be, this one is going to be 1, 2, 3, 1, 2, 3, 4, so it's 3, 4. This one is going to be negative 1, 2, 3, 4, 5, and negative 2, so it's negative 5, negative 2. And what you do is you take this and subtract that. So let's do it as a vector like this. So you'll have negative 5 subtract this one, minus 3, comma, and then you take 2 minus, oh, this is negative 2, negative 2 minus 4, which is negative 8, comma, negative 6, or negative 8I minus 6J. Okay, so that's my position vector. Let me make sure I'm doing that the right way. So it's 1 to A. Yeah, okay. So that's the vector, this vector here. We know Q1, that's negative something or other. Because this charge is negative and this is the point which is with a positive test charge, the actual force vector will be the opposite direction that the position vector is. It's going to be attracted. The positive test charge would be attracted by the negative actual charge. Okay, so now we need the magnitude of vector 1A. So there you just take the square root of negative 8 squared plus negative 6 squared, which is going to be, actually I think it's going to be 10. Just happened to turn, so that 3, 4, 5 triangle. So yeah, you'll get 64 plus 36, which is 100. Square root of 100 is 10. So that's the magnitude of the vector. And we know that Q1 is equal to negative 1.9 microcoulombs. This is meters. This is meters as far as units are concerned. Okay, so let's write down the equation. So the electric field, let's see what the subscripts I used here. Okay, the electric field due to charge 1 at point A is going to be equal to K times Q1 times R1A vector divided by the magnitude of R1A vector quantity cubed. So we have 8.99 times 10 to the 9th. And those units, if you remember, this is going to be force per, what I'm thinking back here is Coulomb's law, K, Q over R squared. Okay, so it's going to be divided by that. So it's going to be Newton meter squared per Coulomb squared. So that's the units. Let me move this thing over a little bit because I'm going to run out of space quickly. Move it all the way over there. Then we have Q1, which is negative 1.9 times 10 to the minus 6 coulombs. Yeah. Times the vector, which was negative 8I minus 6J, all divided by 10 meters cubed. And remember, this position vector has units of meters, so we have meters cubed. So if you look from a unit standpoint, what's going to happen is this is going to cancel out with that and that, because you'll have meters cubed divided by meters cubed. One of these will cancel out with one of those. So the units we're going to have is newtons per coulomb, which is what we expect. And now we'll plug the numbers in. So it's 8.99 e to the 9th times negative 1.9 e to the minus 6. We're going to multiply by negative 8 for the x component and divide by 10 cubed. So what we get is we get positive 136i, and we'll also get positive here because we have negative here and a negative there. Okay, so all I need to do is change the 6 to, actually that was using, oh that's right, yeah, change the 8 to a 6. Hold on just a second. Seems like I've got an extra negative in there somehow or another. Don't know what happened. Let me just pause for a second. Okay, that's right. Negative here, so I'm going to get a negative 6 there. So I'll get a positive 102 J newtons per coulomb. So let's look at that. So if we go over to our diagram, here is the point in question, point A. Here's the charge, charge 1. Let's put a little circle there so I can see that this is a charge. This is just a point in space. So what's going to happen is, at this point, because this is positively charged, the test charge is positively charged, this is a negatively charged particle, they're going to be attracted to each other. And so the electric field vector should be in that direction, which is positive x, positive y, and the y component should be smaller than the x component. So let's look at that. The y component is smaller than the x component. So that's pretty much it as far as how you do it. And if you have more than one charge, which is what you'll be doing an example here in a second, is you just do these separately and then you add the two vectors together. The two electric field vectors due to the two charges. Just add them together to get the resultant vector. That means adding the components together.